solving system of linear equations. Let's revisit this topic. In the previous session, we looked at the matrix method of solving system of linear equations. So let's very briefly review what we did. We had this system of equations which we wrote it using matrices, where A was the coefficient matrix, X was the variable matrix, and B was a constant matrix. Using these matrices, we write this system of equations as A times X equal to B, so that we can solve it by taking the inverse of A. So the left hand side, A inverse times A becomes I sub n, which multiplied by X gives us X. Whereas in the right hand side, we have A inverse times B, which means we have to evaluate A inverse. So now how do we find A inverse? So for that, we had looked at the process to be followed, and we followed this process. So write the submatrices, determinants of the submatrices, that is minors, build the cofactors matrix, transpose the cofactors matrix to get the adjoint of A, and then use this formula to find A inverse. That is 1 by determinant of A times the adjoint of A. And finally, we had the solution. X, Y, Z is equal to minus 2 by 3, 49 by 3, and minus 10. Now, let's look at another method of solving such systems called the determinant method or the Cramer's method. So here again, we are going to use the same system, right? Because then we will be able to verify whether we get the same solution. Now, first of all, we evaluate the determinant of the coefficient matrix. So coefficient matrix is A. So determinant is 3. And by the way, this notation is also used for representing the determinant. So we have another notation for the determinant, that is delta. The next step is to replace the first column with the constants. So 1, 2, and 4 gets replaced by 3, 5, 1. Now what are 1, 2, 4? Remember, they are the coefficients of X. So coefficients of X, we replace it with 3, 5, 1. And we evaluate the determinant. And let's represent this determinant using delta 1. That means the first column has been substituted. Next, we repeat the same process with respect to the coefficients of Y. We replace them by these constants and evaluate the determinant and represent it as delta 2. Really, the next step is we replace the coefficients of the third variable, that is Z, with the constants and evaluate the determinant, representing it as delta 3. So now value of X will be equal to delta 1 divided by delta. Delta 1 is minus 2. Delta is 3. So X equal to minus 2 by 3. And we have here, see, matrix method, minus 2 by 3. Y is equal to delta 2 by delta, which is equal to 49 by 3, which is what we had. And Z is equal to delta 3 by delta, which is equal to minus 30 by 3, which is equal to minus 10. Again, which matches the result from the matrix method. And remember here, we are dividing delta 1, delta 2, delta 3 by delta, which means delta cannot be 0. So that is the Cramer's method, which actually makes it very easy to solve the system of equations compared to the matrix method. Matrix method, major part of the effort goes into figuring out the A inverse itself with so many steps. Cramer's method reduces that effort to a large extent, but again, only to a certain extent. That is, when we are talking of 2 by 2 or 3 by 3 matrices. So Cramer's rule applies to all systems whose coefficient matrix is an invertible square matrix, but it is mainly used for small systems due to computational complexity. For higher order systems, we simplify matrices to equivalent forms that are easier to handle. You might have noticed that every time we have to evaluate the determinant, we end up looking at or evaluating the determinants of submatrices or subdeterminants. So that is where the complexity comes. So that is where we need to come out with some newer techniques by which we can arrive at equivalent forms that makes it that much more easier to solve these type of systems. Okay, that's it for now.